Hello and welcome back. In this video we will look at segmentation of brain tumors from magnetic resonance images using some of the deep learning techniques, especially CNNs that we have seen so far. So, brain tumors or gliomas, so we typically refer to them as brain tumors. They affect the central nervous system, or they usually are in the brain, and this is a serious illness, form of cancer which has very poor prognosis, in the sense the survival is less than 2 years, and the patients are typically monitored by magnetic resonance imaging, also referred to as MRI, magnetic or MR imaging, or MRI as it is known as. It is a, like all imaging techniques, most imaging techniques, it is non-invasive, non-ionizing radiation is used, basically a magnetic field and you have RF excitation, that is what enables the imaging. It has very good spatial and temporal sub-millimeter spatial resolution, and in this case temporal resolution in this case is not very important, but spatial resolution is good. So, the idea behind imaging these patients is that by imaging them you can visualize the tumor non-invasively, and by looking at the tumor, measuring its size, doctors usually use that as a as a marker for figuring out if the tumor is progressing or if it is responding to medication, in this case treatment. So, the segmentation or delineating the pixels corresponding to the tumor is an important task, diagnostic task that way. It is typically done manually by an expert radiologist. However, it can be very time consuming, and there is some variability among the radiologists on certain tasks. And if you have very large patient database, if you want to do like a meta-analysis or anything, then manual delineation is exactly not possible. So, in order to augment a radiologist's effort, it is a deep learning program that can effectively segment the gliomas can be a very valuable tool. So, typically not one image is acquired, but volumes are acquired. So, typically MR image volumes, MRI, it is called MRI image volumes are acquired. We will not go into the details of the acquisition or the physics behind the acquisition. These are image volumes. When I say image volumes, they are basically 3D arrays. So, each image is a 3D array. So, typically you would say 256 cross 256 cross 100. Okay. Okay. So, this is the in plane size and this is the depth. Okay. So, it acquires the across the anatomy. Okay. So, and in the form of slices. Okay. So, in terms as far as MR is concerned, MR imaging is concerned, multiple image volumes are acquired, and each image volume corresponds to what is known as a sequence. Each sequence corresponds to a certain technique or a certain way of exciting the spins inside the human body, exciting the magnetic spins inside the human body. So, that each of them give rise to a separate kind of grayscale contrast in the image. So, if you look here, we have shown 3 types of MR images corresponding to the same anatomy. I am just scrolling through the anatomy automatically, and you can see that each of them, we do not worry about the meaning of these things right now, but you can see that each of these images, even if they pass through the same anatomy, they have a different grayscale contrast. Okay. So, multiple different types of contrasts are possible using MR images. So, for a typical glioma imaging session, you will acquire about 4 such sequences, and each sequence will have size of 256 or 56 times 100, where 100 is the number of slices through the anatomy. If you are wondering where that 100 comes from, so let us say there is a typical human head right here. Okay. So, brains right here somewhere. So, you would acquire slices which cut through the brain, okay, or the head, so that you cover the entire brain or the entire head in this case. Okay. So, just to reiterate, every MR image is actually a volume, it is a 3D array, and you will acquire typically about 4 such 3D arrays per patient for diagnosing gliomas. So, typically a glioma, this is in line with some conventions that have been laid out. It is divided into these 4 subcompartments, this edema, necrosis, enhancing tumor and non-enhancing tumor. If you see the image below, if you see in this image, the tumor is delineated this way kind of, right. The green regions are basically what is known as edema, which is some fluid or water accumulation, okay. And this also tells you why we need 4 different sequences, because certain components of the tumor are seen much more clearly in certain sequences. So, for edema is seen very well in FLAIR and T2. The necrotic region where the dead cells accumulate is seen very well in T1 post contrast or T1C, this is always referred to as T1C. The enhancing tumor also, which indicates breakdown of blood brain barrier, is seen in the T1, again seen in T1C. So, if you look here, the enhancing tumor is these regions marked in color, okay. The necrotic regions are once again marked by different color here in another sequence, okay. Non-enhancing regions are those regions which are neither of the 3, okay, and again there is some variability among radiologists as to what these regions are, okay. So, the final segmentation akin to semantic segmentation that we are looking for is given by this image. You see, we need about 4 classes of pixels that we want to delineate. Of course, what is left out here is the normal. So, everywhere else here, all the pixels here are normal pixels that correspond to a different class completely, okay. The classes within the pixels are the edema, enhancing tumor, necrosis and non-enhancing tumor, okay. So, this is the task. So, what does the data look like? So, this data is part of the brain tumor segmentation challenge, which is conducted every year as part of the medical imaging conference called MICCAI, MICCAI, okay. It is conducted every year in a different city in the world. It is one of the conferences for medical image analysis task, and this particular challenge has been, this is one of the more popular challenges. You get a lot of people entering it, trying to win that challenge. So, its acronym is BRATS. So, the data set is publicly available. It is a multicentric data set. So, to elaborate it briefly, it is multicentric because MR imaging is the grayscale values or the contrast that you see in the values, and some of the artifacts or shading that you get in the images vary from scanner to scanner and from hospital to hospital. So, it's important to get data from different scanners or different centers like different hospitals, so that your network generalizes well to some new data from a different hospital, okay. So, it is very important. There are 2 types of gliomas, low and high grade, okay. So, high grade glioma is the more serious condition. Of course, typically most low grade gliomas progress to high grade gliomas. We are not talking about diagnosis here, just to understand that there are 2 types of them, and the tumors in them do look different. So, it is important to understand that they are indeed different delineations required. And so, in the sense that when I say they do look different, if you train a network on high grade glioma, it is quite possibly not going to work very well on the low grade glioma. That is what I mean by different, not so if you have to talk to a radiologist to get really to understand the pathology difference between low grade and high grade gliomas anyway. So, each patient volume consists of 4 different volumes from 4 different sequences, okay. So, we start the FLAIR sequence, fluid attenuated inversion recovery, T1, T2. These are the names of the techniques used to acquire the volumes, and if you see on the panel below, you see that again each technique gives rise to a slightly different, or in this case radically different grayscale contrast that helps the radiologist identify the pathology in the tumor, in the image, as well as the different types of pathologies. We will not go into these things which I have mentioned here, which is each MR sequence is skull stripped. So, typically the skull is also imaged and generally interferes with a lot of the processing. You would typically try to remove that. They are registered in the sense that not all patients do not have the same head orientation during the acquisition of these different sequences. So, there will be slight differences in the orientation. So, you correct for the pose, if you can call it that, and they are all resampled to have isotropic resolution. In this case it is isotropic resolution, okay, about 1 millimeter cube resolution. Okay. The dimension of each data set, that is each volume. So, you have 4 volumes each of size 240 cross 240 cross 155. Okay. So, typically you can slice this along any axis. So, since it is a 3D, you can, when we are looking at the 240 cross 240 cross sections typically, but you can slice this, and the 240 cross 240 cross section is what is referred to as the axial, and then 2 other perpendicular cross sections are defined, they are referred to as coronal and sagittal. We will not discuss those further, but you can look them up to get a better understanding. So, typically you have this sequence of images per volume and you have 4 such volumes, and ground truths are given for these data sets 210 plus 75. The ground truths corresponding to the color map to the segmentations we saw earlier, and it is also shown on the right here. If you see, yeah, so each of the tumor class with intra-tumor class is marked by a different color, and the task is to obtain a similar classification by using some machine learning technique or other image processing techniques. So, we will typically explore the CNNs that have been very successful at this task. Okay. So, the first CNN that we will look at was this is corresponding to this publication here. It's 2000. This was one of the winning entries to the I think the 2015 competition. Here they used a CNN trained on 2D patches. So, if you recall from our discussion on semantic segmentation, one of the naive ways of doing semantic segmentation is to extract patches from your images and label the center patch according to the image class. So, that is the typical strategy followed here too. So, you have a training set here, 4 sequences, okay, and you extract a patch centered on a pixel. So, in the sense you will extract the patch from all 4 sequences. So, your input is 4 channel with the patch corresponding to each of the 4 sequences, and you will only look at 2D patches, not 3D patches. We will look at 3D patches later. Okay. And of course, the ground truth corresponding to that, you have it, and prior to extracting the patches, there is a lot of pre-processing done, because these MR images are from multiple centers. So, there is a histogram matching step just to make sure that the intensities in the images. So, if you say, let us consider an intensity of 100 or some anatomy in the brain which has an intensity 100, you would want that to be 100 in all the images. So, just to do that, you do some histogram matching to match the distributions of the pixel values across the image volume, across the data set. So, there is a patch extraction and pre-processing steps done, and you train it with a CNN corresponding to a loss function. Okay. So, this is a classification task. So, an appropriate loss function is used. Okay. And then when you infer or during the testing phase, you use the trained CNN to get your final output label. Okay. So, here the labels, there are one of 5 labels, right. You would have background label and you have the 4 classes inside the tumor. Okay. So, the network used is inspired by this VGG network. We have a succession of convolution layers followed by max pooling, and as you go, so these 2 layers have 64 filters defined, these layers have 128 filters defined. Okay. And you have a max pooling layer with stride of 2, and then you have fully connected layers, and you have output here 5 class output. Okay. So, this particular group trained 2 networks, one for high grade glioma, the other one for the low grade glioma. So, it's actually the other way around. This is the low grade glioma network and this is the high grade glioma network. If you can see here, the high grade glioma network has slightly more number of convolutions, in this case 3 convolutions of 128 with 128 feature maps defined, and then a max pooling layer, as opposed to here the number of convolution layers here is only 2. This has 3 and it has 2. So, there are 2 successive convolutions with 128 feature maps, and there are 3 of them here. So, they train networks with data corresponding to low grade and high grade with these 2 networks, and they had the most competitive performance for the segmentation challenge. This was in 2015 is what I recall. So, this is inspired by VGG. So, but the number of filters and the number of layers is much different. Okay. You can also understand that you can't have a network as deep as a VGG network because we don't have as many points, data points, and we are training. The training was done using patch, as we saw earlier, using patches. So, you can actually typically extract, since the size of your input volume is 240 cross 155, and you typically this group extracted patches of size 33 cross 33. Of course, there are 4 sequences. So, your input has 4 channels with patches of size 33 cross 33 extracted from each of the sequences stacked together. That is your input. The output is to classify the center pixel in that patch as belonging to one of the 5 categories that we saw earlier. Okay. So, the 5 categories being it is a normal tissue, enhancing tumor, non-enhancing tumor, necrotic core and edema. Okay. So, these 5 classes, these are the outputs, and this is inspired network inspired by VGG. So, this is one of the earliest CNN used for this particular task. Okay. That won the challenge again, and as you can see, some takeaways here being you use the architecture that is used in ImageNet, is inspired by the ImageNet VGG architecture, and it's patch based training so as to label the center pixel. And of course, this entire network was trained from scratch, no weights were used from the VGG network, and you also they also had to do data augmentation by flipping rotations and translations. Just to summarize, once again the idea is to use patches of size 33 by 33. They are, and they have 2 different networks, one for the low grade and the high grade glioma, and the network is trained to classify the center pixel of the patch, and following that there is something called connected component analysis, wherein you retain the largest connected component of pixels. Connectivity is defined as 4 or 8 connectivity. So, if you have a grid, let us say in this case easier than 3 by 3 grid. So, if you label these pixels of belonging to a class, right, they are all connected, so you retain them. Let us say somewhere else in the image you have one isolated pixel and you typically tend to ignore it. Okay. So, you would group the pixels depending on how, if they are all connected, and then remove those pixels that are not connected, in the sense that you find the largest connected component this way based on this kind of connectivity, and actually remove those other groups. Even though they are connected, they are much smaller than this, so they are removed. So, by retaining the largest connected component, they were able to get very good scores. So, these are the typical segmentations that you get from the network. Another approach to this problem is using a UNet architecture we saw earlier. So, here we can actually predict an entire slice. We can try to predict an entire slice or an entire patch in one pass, rather than in the previous technique that we saw, only the center pixel was appropriately classified as belonging to one of the 5 classes. So, we can use a fully convolutional neural network. So, one of the entries in the competition, or a encoder decoder type network, which is a unit is one such type, can be used to accomplish this task. So, let us see how that works. So, here you can give the entire slice as input. So, we looked at the once again the size is 240 cross 240, and there are about 155 such slices. This is one slice. So, in the previous network that we looked at, each slice is rasterized. I mean, you have taken a patch of size 33 by 33 and you center that patch on every pixel and try to predict every center pixel of every patch. That takes a lot of time. So, you can using a fully convolutional neural network predict the labels of the pixels in one forward pass through the network. Okay. So, this is a typical unit architecture that we have seen earlier. Okay. So, it takes as the input 240 cross 240 and predicts the class associated with all of the pixels. So, it has an encoder and decoder type of architecture. This you have seen through before. So, this is the downsampling layer and this is the upsampling layer, and there are these skip, if you can call them shortcut connections or skip connections from the downsampling layer to the upsampling layer in order to improve your resolution. Okay. So, again the skip connections were used to combine the low and high level risk features in the network. So, this was one of the entries to the competition, and the citation is at the bottom of the page. You can look them up for more information. Of course, here this might not be the most incredibly efficient way of doing it. The better method would have been to predict, let us say, a smaller area within the network. Okay. Because as you see, there is not enough information. There are the two problems here. If you noticed, we have mentioned earlier, the images are 3D. So, these are not 2-dimensional images, these are 3-dimensional images, and it is more meaningful to process them as such. So, the slices, successive slices as you go through the volume are correlated. So, it is good to exploit that correlation. And within a slice, so if you look at a one cross section, that is one slice that is shown right here, there is not much information about what this class, at the edges of the image you are losing out, because the neighborhood information is missing because you are close to the edge of the image. So, it would be more meaningful just to have predicted, let us say point out some smaller area inside the box, inside the image, even using a unit, that is more meaningful. So, you can always take a crop and combine and use that in the skip connections rather than using the entire feature map, size of the feature map. So, it would have been more accurate that way. And another thing to point out is that we are not considering the volume, the image volume, rather we are only looking at the cross sections individually. Okay. So, these are the results from that UNet segmentation network. As you can see, quite a few false positives, which, as I mentioned earlier, if you do connected component analysis wherein you retain the largest cluster and you can get rid of the smaller ones. So, that is a good analysis. On top of that, you can also do conditional random fields, okay, but it is not done here. But if you look at the prediction after post processing, which is typically connected components, and compares very well, qualitatively in this case compares very well with the ground truth annotation. In this video, we will look at another architecture for brain tumor segmentation. It is called the 2D tiramisu with 103 layers. Okay. So, basically it is inspired by DenseNet architecture. It has a dense blocks, transition down and transition up blocks. The dense block has 3 layers, 3 convolution layers, and each layer has a composite operations consisting of batch norm, ReLU, 3 cross 3 convolution and a dropout layer. Okay. The transition down layer, wherein we are subsampling the feature maps, again as batch norm, the ReLU nonlinearity, 1 cross 1 convolution, again a dropout layer has been added here during training, followed by max pooling. The transition up layer has 3 cross 3 transposed convolutions, it is tried of 2, and we try to, and the network actually predicts the entire input in one pass through the network. So, the dense block, as we seen before, series of convolution layers, and each layer receives input from all the previous layers. So, just in order to prevent the feature maps, too many feature maps, and if there is feature map explosion, we control the growth factor to 4. The transition down layer, as you saw before, is used to reduce the spatial dimension of the features. It's used in the downsampling side of the network, and the transition up is the transposed convolution layer used in the upsampling side of the network. Okay. So, the typical architecture is given here. So, you have 4 channels as input corresponding to the 4 different MR sequences, each of size 240 cross 240, and then of course followed by there is an initial convolution, okay, which leads to 48 feature maps, followed by a dense block and a transition down block. When after the transition down block, you have the feature map size is reduced to 120 cross 120. So, you go on, you have several, about 1, 2 and 3, 4 dense blocks, gives rise to a 15 cross 15 feature maps with 464 of them. Then we have a bottleneck layer which does the 1 cross 1 convolutions and a transition up, and then again we go through the transition up layers, which again has 1, 2, 3, 4 dense blocks in between with and interspersed with transition up blocks to get an output of which has a 3, in this case we are predicting 3 classes, and you can do an argmax across the classes to get a 240 cross 240 output. Okay. The reason why this is there are only 3 classes instead of the 5 we saw earlier is because some of the classes were merged in this version of the Brad's segmentation challenge. So, we ended up predicting 3 classes. The other architecture that we're going to look at, it's called Deep Medic, from a group in UK, and they exploited the 3D nature of the input data. So, the slices are correlated across a volume, and of course, since your volumes of size 240 cross 240 cross 155, it is not possible to give 4 such volumes as input to the network. You will run out of memory eventually, since you remember that you have to have mini batches and all that during training. So, the idea is to restrict the size of the patches so as to not have a memory issue, but at the same time exploit the 3D nature of the images. We just briefly look at the architecture used. This was again the winning architecture 2 years in a row, I think 16 and 17, 2016 and 2017. So, this group use 2, citation is at the bottom. This group use multi-pathway or 2-pathway network. So, one pathway is supposed to give local features at high resolution, and the other one gives global features at low resolution. So, the local features are learned from 3D cubes of size 25, so 25 cubes and 4 such channels. Well, the global features are learned from patches of size 51, but then resized to 19 cubes. So, the large green box is the size of the 51 cube size, 51 size patch, but then it is resampled to 19. Okay, but it is a 19 cross 19 cross 9 volume from inside the image. Of course, there are 4 channels, you have 4 such cubes, and then you have sequence of convolutions, and then there are also in between there are these ResNet residual layers like in the ResNet architecture, and then finally the lower pathway, which is the global feature pathway, is upsampled and concatenated, and then you have the usual convolution or fully connected layers, which leads to and the usual fully convolutional layers, which leads to an output of size 9 cubed. So, the output size is 9 cubed. So, you are taking a very large context, which is typically 25 cubed, and you are predicting 9 cube out of it. Of course, there are 5 classes, so you have 5 cross 9 cubed outputs, each giving the probability of that particular class. So, this architecture was very efficient and it won the challenge 2 years in a row. It incorporates several things. One is that we need 3D context, especially for medical images. That is very important because the images are inherently 3D. So, it is good to exploit that. It uses two pathways. One pathway looks at a higher resolution, but a smaller patch size. The other pathway looks at a lower resolution or the global features, but with a bigger patch size. So, you resize the 51 patch to a 19 cubed and you do a sequence of convolutions, max poolings, as well as these skip residual connections to improve training. And so, this particular architecture incorporates and of course, incorporates both those concepts that I mentioned earlier, and also that instead of trying to predict the entire image in one pass, right, you are trying to predict only smaller cubes, of course then smaller volumes, but then you do have to then raster through the network in order to obtain. So, it is not one pass to get the entire volume, but multiple passes, because you are only eventually predicting a 9 cubed. Okay, so, you are predicting a small subset of pixels inside your patch that you have taken, but then you are considering information from a very large neighborhood of the patch that can, and that is easily handled by the network. They also have the conditional random field regularizer at the after the predictions. So, if you look at what you have seen, these images show the manual, this is the ground truth and this is the net output predicted by the network. Okay. So, the CRF is used to regularize your output predictions. So, that is one of the other novelties in this particular submission. So, a variation of that, not like in the sense of just using 3D patches, is the 3D tiramisu network. Okay. The building blocks are very similar to the 2D variant, however, the patches are 3D in nature. So, instead of using the entire 2D volume as input, you take 64 cube patches as input and you try to predict all of them in one pass through the network. Okay. One of the challenges in this brain tumor segmentation is that there is a huge class imbalance, which is finally as a final talking point in this application that we are looking at. So, if you typically look at these images, you will find out that some classes are wholly underrepresented. So, for instance, the non-enhancing tumor or the necrotic core comprises of a very small number of pixels corresponding to the tumor itself. Now, if you consider the tumor itself, it occupies a very small volume in the entire brain. So, less than 5%, I am being, it's a very conservative estimate, less than 5% of the tumor in the brain actually corresponds to the tumor. Okay. So, that is the class imbalance. So, if you are trying to do a pixel wise classification, you will see that most pixels are normal, right, and a very small percentage of the pixels actually comprise the tumor itself, and within the tumor itself there are these classes which are very underrepresented. Okay. So, these considerations one has to take care of when you train these networks. So, for instance, if you should make sure that your cube, that the cubes you are sampling, or if you are doing a patch based approach where you are classifying center pixel, then you should sample or do more data augmentation for the underrepresented classes and train the network accordingly. Okay. So, all the networks we have seen so far using either 3D patches will suffer from it to varying degrees. So, the advantage with using 3D patches is that this class imbalance is slightly alleviated, because if you are looking at a slightly large volume through the tumor, then the volume will contain enough samples of every class. That is a general observation that we can make. So, doing 3D sampling, doing 3D patches for medical image, unless in this problem, at least the problem that we are looking at, alleviates the class imbalance problem to some extent. So, of course, you can always sample so that you have the underrepresented classes have more samples to match those classes that are overrepresented. And typically we also see that many of the techniques use the connected components to gather the largest connected component, or they do a conditional random field approach to clean up the segmentation, because the cleaning up requires, in the sense that there will always be false positives, some pixels, some small clusters of pixels or groups of pixels being labeled as tumors when they are actually normal. So if you want to remove those, then you can either do a connected component or a CRF. CRF takes into account the context, so that's a better way of doing it. But most research groups aim at not trying to do this post processing, and rather just use the output from the network itself as the final result. Okay. So you can see the impact of the post processing here on this particular segmentation. So if you look at the post processing, so this is a post process image, that this particular small region has been removed corresponding to one of the classes, and it matches very well with the ground truth right here. So post processing does help improve your score a bit. And when you are doing this 64 cube patches, the stride at which you sample also seems to help. The overlap, the stride with the overlap, in this case 32, especially found to be useful for classifying the boundary voxels in the patches. So segmentation with stride seem to be more smoother than unstrided approach. So that's something that we have observed in our experience. So post processing is of course necessary in many cases, depending on how accurate your network is and the amount of false positives that it generates. That's an important aspect of the processing pipeline. So that concludes our case study. We were looking at using convolutional neural networks for analyzing medical images, specifically to segment brain tumors from MR volumes. A particularly challenging problem, since brain tumor is diffuse, there are no clear-cut boundaries in many cases, and the problem also involves segmenting subclasses from the tumor, which are again not that well defined in many cases. The size of the data set is also a challenge, since these are inherently 3D data, and every patient or every data point is actually made up of 3 volumes or 4 volumes, and how to extract patches from those volumes, whether 3D or 2D, and train them also to do the inference more efficiently, so that if you get a patient volume, you should be able to do that in a reasonable time. That is also an important requirement, both accuracy and efficiency in computation. So that concludes our session on CNNs. So we will move on to other deep learning architectures in the subsequent lectures. Thank you.